that they similarly do an aerobatic ride of some kind. And this one looks like they either pilot became incapacitated somehow, or it tore a wing off. Because it looks like it hit pretty direct on the vertical. But nothing but a 4-foot hole and a 1.5 feet deep, and a bunch of shredded aluminum and burnt ground. So hopefully it's pilot error and not maintenance error. Can't say yet, but given that they've had two similar problems or 2 incidents, I don't know if they're related at all. But, I tried to find a little bit more about the prior one. I didn't find anything NTSB on it though, so. No. My guess though is that because they've had 2 incidents, the FAA is going to be looking pretty thoroughly. Okay, so in the interest of not spreading words, what we'll do is I'll go over this, the homework, but I'm not going to hand any out, just so I don't give you my cooties. I'll do my best to sneeze in the corner and not blow bubbles all over you. Okay. All right, so this is a little bit of a slightly different kind of problem. Comes down, goes back to here, overload up to there. One there. One there, oops, I forgot one here. One there, then it looks like it's got another path here and another path there. So 1, 2, 3, 4, 5, 6, and 7. So we go total 1, 2, 3, 4, 5, 6, 7. Voltage, current, resistance, and power. Oops, just a little bit more. Line there. All right, so we were given some values. That will work better. We were given some values. That's not power total. 0.585 watts. 0.0. Whoops, 0. Oops, I'm off by 1. 0.1648 watts.
You're off by 1 board.
Oh, okay. I am off by 1 board. That's what I did. So, oh, well, I see what I did. All right. Let's move those. We'll move those out. Voltage, current, resistance, and power. 5.85 watts, 0.1648 watts, 0.0974 watts, 2.068 watts, 0.3264 watts, 0.1183 watts, and then nothing here, but up here, 390 ohms, and a voltage drop of 0.74 volts. So that's what's given. All right, so first thing we need to observe is we have a bunch of parallel paths in this circuit. However, we have some parallel paths that are apparently no-load parallel paths. So between 4 and 5, we have 2 parallel paths. After coming off of the 2 different nodes between 1 and 2 and 2 and 3. We also have 2 different parallel paths between 5 and 6 on theoretically the ground side. Now, unless we had a whole bunch of current going through there, those 2 parallel paths don't mean much, do they? Okay, those are just distractors. I could continue to make parallel paths. Here, I could even draw one across there, one like this, one like that, one like this, do all kinds of neat things. Okay, it wouldn't really change our equation that much. Unless it was a very, very high current path to the degree that any of the conductors also created a little bit of a voltage drop. They were starting to get warm and creating a little bit of a voltage drop. So for the perspective of our diagram or our work in this problem, we can just disregard all that. So let's see, the second thing that's going to matter to us is about the only calculation. We can almost calculate power total, right? But not quite. We need at least one more ingredient to be able to add that up. However, in column 7, we could calculate power total either by using the one odd derivation of Ohm's law or by calculating current total through number 7. If we calculate current total through number 7, doesn't all the current that's going through the circuit have to pass through 1, all the other stuff, and through 7, and back to the battery? So once we derive the value of current for 7, we can then plug that into current total and current for number 1. Okay, so let's see, 400 into 50. Let's see, 50 is what, 1/8 of 400? So it's going to be something fairly small, 1/8 or 0.125, something about like that. Well, survey says here 0.130. Let's see, yeah, 1301 seems to be the common. That's pretty close to 0.125. Okay, 0.1301 amps. So now I can go down here and I can plug it into current total, 1301 amps, as well as plug it into here. Now that I'm in the right column. All right. So now I can do a couple of things. I could solve for power and then add all that up to get the power total. So let's see, 10% of, you could say that 0.1301 is something slightly more than 10%, 13% of 50. Well, 13% of 100 is 13, right? So 13% of half of 100 is going to be 7.5%, right? So then you would, that would then become your power there, or 0.1 this case, this person came out with, well, yeah, survey says 6.6, 6.59, 6.601, 6.6014. So yeah, that's about right. Okay, so 6.60104, something like that, watts. Now, if we look at the rest of these, we can pretty much say that all the rest of these resistors are probably pretty high resistance value because the amount of power that they're consuming isn't that great. We're consuming 6 watts on 7, or almost 7 watts on 7, and almost 6 watts on number 1. Okay, all the rest of them end up in parallel circuits, so the current that's going through is being dropped quite a bit on those. Let's see, if I add all that up, what am I going to get? I'm going to get about, let's see, 6, 8, 8 and 12, 13, 14, maybe 15 approximately, give or take a little. 15 watts, give or take a little. Well, that didn't do too bad for what rough guessing. Survey says 14.9611, 961. Okay, 14.961 watts. That seems about right. Okay, again, rough estimating, but then using what you guys did calculation-wise, that came pretty close. So now, how many times would let's see, if I did, how many times would 0.1 go into 14.96? 149 times, right? Right. So 0.13 is going to be something less than that. So my guess is we're probably in the neighborhood. It's substantially less, so it might be like 120. I'm just rough guessing, 120, 130 volts, something like that. Oh, it's a little bit less. Survey here says 114.9997. So it looks 115 here. So yeah, it looks like the voltage here, total voltage is going to be 115 volts. Okay. And again, ballparking, that's about right. Same thing now. We're going to need to, we can finish out, we can get R sub T, or we could do it the other way, calculate all of the different resistances, and then cross-check it. So maybe we could do both. Certainly 115 divided by, again, 10% is going to be, would be what, 1150, but it's 1150. However, it's going to be a little bit less than that because it's actually 13%. So it's going to be, I'm going to say maybe 950, 960 ohms, somewhere in there, some approximate value. I guess I missed a little bit here. Survey says 883, so I was off by a little bit. Again, just rough guessing. So looks like 883 point, we'll call it 896 ohms. All right. So for number 1, we know what the power is, and we know that the voltage drop across number 1 cannot be more than 115 volts. Okay, can't be more than source voltage. Has to be something quite a bit less. In fact, we also know that we're dropping 50.74 volts across number 7. So that's almost half of our voltage. So in truth, the voltage drop across number 1 couldn't be more than 65 volts, right? It's probably going to be something less. You know, my guess is it's going to be still a fairly good chunk of the voltage is being dropped there. And the reason I say that is the bulk of the power is being consumed here and here, with a little bit more there being dropped right across number 4. Okay, all the rest of them aren't using that much power, so the voltage drop across those are going to tend to be the least amount. So my guess is, just looking at that number, I would say, and I'm thinking about preferred resistors, so it would either be 330 or 270, because those are the next 2 preferred resistors below. Actually, no, it's the other way around. What am I saying? It'd be higher. So what's higher than what's the next preferred resistor from 390? Isn't it 470? Isn't that the next one up? That would be my guess, just rough guessing. And so dumping that in, 558, yeah, that would make about sense. Oh no, it was the other way. I was going the right way the first time. Hold on, wait a minute. Let me think about that. I guess I was right the first time. Now, survey here is giving me 329.96, 330, 329.98. So, again, so 330 makes sense. 330 ohms. And that times that is going to have to be less than whatever's left over. Say 65, 55, well, it's a smaller amount. So, given that's a higher resistance by what? By about a fifth. So I'm going to say it's probably maybe 40 volts drop, 41, 2 maybe. The survey says actually 43 or 42.92. Okay, just comparing the resistance drop here, since I have the same amount of current going through both of them, this one's going to drop a little bit more than that one. This was at 50, and the difference between the two is about 60. 60 is going to be about a fifth of that, a fifth or a sixth, somewhere in there. Okay, so a fifth of 50 is pretty easy to figure out, right? That's 40, plus a little bit. So rough guessing, I came up with something close. And again, for you guys, you should be able to estimate something close to what you should be expecting. Let's see, 9.3, I'll round it up, and that's volts. So now what are we going to do? And this is where some of you, at least in the earlier class, had some difficulties. We're going to have to do some analysis at this point, right? We can't do any more math based upon what's available on the chart. So at this point, we're going to have to say, we've done voltage drop across 7 and 1. So we started out 0 there and 115 there. We've dropped it, what is it, 42.93 here. And we've jumped up 50.74, right? That correct? So 115 minus 42.93 is what? Well, you can do it that way, but what I'm really trying to do is just get to the node voltage right there. Then we'll subtract the two. Okay? So in truth, this isn't the actual node voltage. It's actually 115 minus this gives you the voltage there, right? Okay, so let's see. 40 from 115 is going to be 95, 75, 74, 73, 72.07.
Mm-hmm.
Okay, so the actual voltage here is going to be 72.07 volts. And I've got 50.74 volts down there. So the voltage being dropped across 4 and 25236 is going to equal the difference between those two, right? We're all okay with that?
You forgot one, right?
Huh?
You forgot one. That's the total voltage dropped and everything but 7, right?
The difference between these two. So here I went up 50, and there I'm down to 72. The difference between those values is the voltage drop across 4 and the voltage drop across 25236, right? So 50.74 subtracted from 72 ought to give us 21 something, right? 21, can't do it in my head because my head hurts. I got 2132, 2134, 2129, 213, 336, all kinds of different numbers here. Well, we're starting to get a little wandering, but that's not surprised. Let's go 29, let's go with 2933. So the voltage drop across number 4, I can't remember, 21.33, is going to be 21.33 volts, approximately, right? Okay, now I can do some math. I don't know that I care what the resistance is yet, but what I do care about is I know what the total current is going through number 1 and number 7. If I can pull out the branch current that's going through number 4, whatever's left, the remainder, has to be going across number 2, right? Bear with me on that. So, approximately 21 divided by, or 2.1 divided by 21. Okay, I mean, if I were to just wiggle that up a little to 21, or to 2.1 and wiggle that down a little bit, I would get total current going through there is about 1/10 of an amp, right? Give or take a little. So the bulk of the rest of the bulk of the current is going across number 4. And then a much smaller portion of it, maybe 1/4 of the current's going out through number 2. So to do that math, excuse me. Yeah, I didn't quite hit 1%, slightly less. I'm seeing 0.96, 0.97, 0.97, 0.969. So let's go, and I lost where I am. 0.9, what do we say? 0.96. Let's just go 0.969 amps going through there. And that represents the majority, maybe 2/3 or a little bit more of the current is going through 4. We could then do the math on that and say 0.1 goes into 21.33, 213 times, but it's going to go in a little bit more, so maybe 220. That seems like that'd be about right. Yeah, I'm seeing 220, 219, 220. I'd say this is probably a 220 ohm resistor. Okay, so now, what am I going to do? So I can take, to get the branch of the branch current that's going through number 2, I can subtract branch current going through number 4 from total current, or the current that's coming out of node, or, coming into this node right here. So the current that's going into that node, I can subtract this, and whatever's left over must be going across number 2. So 1301 minus 0969, so that's going to be 031, 032, so it's going to be 0.0332. That seem right? I'm doing this fast on my head, slightly loaded on data draw. Yeah, that's what others got. 0331, 03317, 0332. Okay. So now from there, I can calculate the voltage drop across number 2. I can also calculate the resistance. Let's see. So 3 would go into 16, roughly a little over 5 times. So going to be something like 5 volts, give or take some, maybe almost 6 volts, right? No, maybe it's the other way. Yep, it is 5 volts, 4.96. Okay. So again, take this value, divide it by that value to get the voltage. All right. So I'm now going to take my voltage drop here, 4.9729. Yeah, that's good. Do the math into there. That's going to be a fairly high number, maybe 470. Is it that high, really? No, it can't be that high. Going into there. Actually, no, it's going to be like 120 or 180. Oh, 150. Okay. So, yeah, 150. Okay, so now what am I going to do? Well, we've got another parallel branch. So I'm just going to do what I just did again, right? I'm going to have to take this 7207. This 50.074 also applies to here and to here, right? But here across that node, I'm going to have to subtract another, I lost it, 4.97, right? To get to the new node voltage. And from there, I can calculate what the voltage drop is at the node 235. Okay, so 7207 minus 4.97 or minus 5 is going to be what? 67.07 plus 3, so 67.1, right? So, excuse me, 68.1. Did I say that right? No. 67.1. Should be 67.10 volts there, right? Did I do the math right? Do it in my head. My head isn't working that well right now. Add 5 to that, it would be 72 minus 3. Yep, that's right. So now I still need to subtract my 5074. I could have also done it the other way, couldn't I? Couldn't I just have subtracted the 497 from here? Okay. I could have done it that way. The reason I'm not is just to make sure you guys understand I'm dropping, okay? So taking 50 from 67, that's going to leave me with 17 minus 26 is going to be 16 or 16 point, what, 84?
36.
16.3, oh yeah, that's right. Okay. Good, yeah, that's right, one more. So 16.36 seems to be the magic number. That's going to be the value of the drop across number 5 and 3.6, right? So 16.36 volts dropped across number 5. From there, I can then calculate the branch current going through 5, just like we did before, and whatever's left over has to be going through 3.6, right? Okay, I don't think I need to do any more. Everybody's got it from there? All right. Okay, so I think I only have 1 or 2 more of these worksheets to do. So next week we'll do the second to last one or the last one. I don't remember what I've got out there, but I know some of you are still struggling a little bit with these, so I'm going to strongly recommend that as I give them back to you, take the problem and change the numbers to the given numbers and rework them a few times. Okay, get practiced up on it. You guys got to be able to do these because you're going to see it not only on other tests from me, but you're going to, at some point, they're going to make you be able to fully explain and possibly even do one of these problems in an oral practical somewhere. And the FAA has long recognized this is a real weakness. Such that they've now created an entire division around it, which is sort of bizarre. Actually, it's sort of funny because the division that they created around it doesn't actually fully understand Ohm's law either.